Welcome. In the previous video, you will learn it about pumping tests, like why do we do pumping tests and how to analyze the results of the pumping test using the graphical method. In this video, I will show you like how to analyze the results of a pumping test using another method like a regression method. And for this regression method, there is like a software we use, like it's called AquatiSolve, and this software it has, as I will show you, it has like all these solutions that we discussed, like the solution for confined aquifer, for confined leaky aquifer, for unconfined aquifer, and so on and so forth. Yeah. And for different cases. And that's why it's convenient to use it. And you don't have to go to like graph and as that is a log scale and read numbers from there or things like that. So it's easy. Yeah. So this software is based, so by the end of this uh, video, you should be able to analyze pumping test data using the regression method. You're not going to use directly the regression method because the software is doing this for you, but it is based on this regression method. Yeah. So so that's how like this regression method work. Like I mean, it's very crowded slide with a lot of text, but the idea is simple. So you have this draw down data with time, yeah? And then you have like a theoretical curve. So that's like your drawdown data here. Yeah. Say like here's your drawdown data. Yeah. And then this is the theoretical curve. So basically you try to find the theoretical curve that will best match this data so that the like so you see here, for example, this theoretical curve well matches this data. For example, like if I moved it here, it doesn't well match this data. There's a big error here. Here. So the ones that match this data, basically, so you keep changing this t value and s value until you find good match between your observed data and your theoretical curve. That's it. Yeah. So basically, it's like so you solve this as an optimization problem. Let me and how that's your objective function. So what's your objective function? Your objective function is you want to minimize the error between what you observe and your theoretical curve, and you sum all like the error here, the error here, the error here for all your points. So that's like you solve it as an optimization problem. So basically, that's what the problem states. This is what the optimization problem state. Find the value of t and the value of s that will minimize the error between my theoretical curve and my observation point. So you can do this with, so here is like with Excel. Again, this is not important. Like this is not an optimization class or a regression class. So I teach this in for undergraduate student in comp tool class. And for graduate student, I teach this like regression method and optimization method in advanced engineering analysis. So that's where you will learn these things. But for that class, it's not important. But that's the idea. See here. Let me show you. That's the general idea. So the general idea is that I want what is the value of t and value of s that will make my observation, like this blue dots, fit my model, my theoretical curves. Let me show you. So here, for example, if I put t is equal to 300, yeah, 3000. See now the curve does not match my point. And see I have like my error. This is the sum of squared error is very large, yeah? Then you can say, okay, I will change my t value to maybe 1000. Oops, now it's going up. So maybe, so now I know it's not like 3000, not 1000, something in between, like let's say 2.5 thousand, yeah? Uh, Not like now, it's maybe a little bit smaller to this one. Yeah, maybe only 2000. Yeah. So you keep doing, see the error is decreasing, means I'm moving in the right direction. Like you see here, this is the sum of the squared errors. That's basically the error between this point and this line. So you see here, I have a big error between this point and this line here, big error here, big error here. So you keep playing. Maybe I will say I make it 1600. Yeah. Oh, now this is better. Maybe I'll say, let me make it 1400. Yeah. Oh, see, this is even better. Yeah. And same, but again, like you have two parameters. You have this guy also. So you'll say I will make this guy like 2 to the power negative 5. Oh, see, now it's going down. So you have to keep playing with these two parameters. I will say I make it like this one, I don't know, 1500. It will drive you crazy if you kept doing this by trial and error, yeah? So it will, doing this by trial and error will drive you crazy. So you can do this automatically, like let's say e to the power minus 5. Yeah, see here, it's not a good fit. And like here, maybe 2000, yeah? It's also not a good fit. So this like see the error is 8098. So you can do this automatically with Excel. Excel can do this. Like if you go here to data, and I put you this is a video from Comp Tool class, I think, where if you want to learn how to do this with Excel. But let me show you. Like you go here to Excel to Solver. You said like my objective is to minimize this guy, like make this guy minimum by changing like with the constraint that like these two guys should be larger than 0. Yeah, so basically the solver will keep changing this guy to minimize this guy. So if we click solve, okay, it didn't work. It didn't find the solution, didn't converge. Let me do maybe it has also e to the power minus 5. Let me try to do it again here, and let me do the solver again. Solve. It's not converging for some reason. Let me. Shouldn't be the case. But anyway, it should work. Like theoretically speaking, it should work. Theoretically speaking, that should work. Like solver. Let's see here. This is your p-values. This is like the objective function. So that's like your objective function here. Yeah. This is your yeah. So you see, this should be like a constraint should be larger than 0, and make and then by changing like which value do I want to change? I want to change like this guy and this guy. So this is my decision variable. So my decision variable is like this guy and this guy. And this is my constraint, like these two guys should be larger than 0. And then if you click solve, uh, and the worksheet became an error when solver tried to certain value validate the cell. So it is giving it an error here. I don't know why. Shouldn't give it an error, but let me do e to the power minus 5. The and this is like sometimes like when your initial value is like is is very close, like is could get like into an error and does not converge when you depending on your initial value. So let's do this 1.5. Select another initial value to start with. Okay, so let's go to solver here. I mean, this. Okay, now we got it. Yeah. So now it's like just keep playing because sometimes the optimization methods that Excel is using could get stuck. Yeah. But here, see, it estimated like this is the t values, this is the s values that will give you the best match, best curve that match your data. So basically, this means that like this is the t and s values that I want to do. And this is what Excel do. Like here, this is a graphical method like we did this last class was a graphical method like when you try to match them visually. Here, like you use an optimization method that will match them for you automatically, and it will give you the t and s values that match this for you. If you don't understand this, that's fine because this is not an optimization or regression class. I just want to show you like for Cooper and Jacob, like this approximate method, you can do it with graphical method, you can do it with also regression method, like automatically using solver, and this is like your homework data. But anyway, so that's how this method works. Like you try to find the S value and T values that minimize the error between your theoretical curve and your field observation. Okay. So this is the graphical method. So from the graphical method, remember you find like WU, you find 1 over U, you find the corresponding S and corresponding T. You substitute them here, you solve for t and you solve for x. So with the graphical solution, I got something that looks like this, 1400, yeah? And this is 2.36, yeah? And this is the R, and this is the Q, and this is this one. Now the regression method, like when I did this with Excel, like last time I got like 1324, and this is 2.1. Like, so you see they are very similar. Yeah, like you see these numbers are very similar. And like, let's see when we did it with Excel this time, what did we get? Remember, this is an optimization algorithm, so each time you run it, it will give you a different solution. It might like here, so for the regression method, we got something very similar. Like, yeah, we got like something very similar, almost the same, yeah. Now, Aquatisolve does the same thing. Like whatever we did here, like solving this optimization problem, minimizing the error between this one and this one, that's what Aquatisolve does in the background. So I just wanted to show you this step. Again, if you want to learn more about it, about how Excel does optimization, you can watch this video. If you want to learn more about like how I plotted like these two curves, you can follow up like the details here. These two like graphs, and then like you play with this two value to find the best match. Yeah, that's it. But I want to show you like with Aquatisolve, like we got the same, almost the same. Like see with Aquatisolve, we got the same results that we got this time, almost the same. 1325 2.1 1325 2.1. We got the same solution. Okay, so that's basically the objective of this video, is not to show you like how to do this with Excel, but the objective of this video is that to show you like how to do this with uh, but this is like a very easy and widely used software to analyze your pumping. Like, so you go to the field, you collect your data, and then now you understand what this software is doing, yeah, in the background. And then in this lesson, we will learn how to use this software. That's very simple and easy to use. Okay, so you start the software, you can download it from online. Like the demo version is free. The demo version, like with the demo version, you cannot. So once you, oops, me, like when you open it, it would look something like this. You can download the demo version. The demo version is free. And the only thing I think limitation with this demo version is you cannot save the answer. But I will show you, like you can, like for your homework submissions, like since you are just using this for education, yeah, purpose. So for your homework submission, you can just take snippet of your solution and just that should be good for your homework submission. Yeah, don't need to save it. But anyway, so you start like in a new project, and I provided also like a tutorial here. So this is an Aquatisolve tutorial, like the class exercise, and I provided like these steps one by one, yeah, to the final solution. But anyway, so you start like this, you start here, it will tell you like you select pumping test phasers, that will do everything for you. Now it's telling you here, I don't know if you can read my screen or it's too small, multiple test drawdown measured in an observation well or a single well test. Remember we talked about single well test where drawdown measured in the pumping well only, as we saw in this video, yeah, in this tutorial videos that I showed you. So you select multiple wells because here we are observing this at a different, like we are pumping from one place and we are observing drawdown at another well. And this will tell you, like you click next here. Here you select your units. So like the units that I have for this problem is the length is in feet, the time is in minutes, the Q is in gallon per minute, and the hydraulic conductivity values that I wanted at the end should be like feet per day. Okay, not sure, yeah. And then here you just put like your information. So like for this one, I will put just like class exercise, yeah, title. You give like a title for your project. You can put like all these other data as needed. Here it will tell you the aquifer saturated aquifer thickness. So like remember this one. So here is our problem. So the saturated aquifer thickness, that's 48, and that's the pumping is 200 120 gallon per minute, and the distance of your observation well from your pumping well is 824 feet. Yeah, and this is the data that what we recorded in the field. Okay, so let's go back to our aquati solve. So saturated thickness, that would be like 48. Here, if you have anisotropy, like we don't have any anisotropy, so we just select one. And that's the good thing about this software is that you can account for these factors, yeah? Now it will tell you the well, like, so you start by the pumping well. So this is the well where I am pumping the water. So I will call this like pumping well. And the well coordinate is like 0, 0. Now it tells you about the well configuration, whether it's like a fully penetrating, partially penetrating, vertical piezometer, or horizontal, like a horizontal well. Yeah. So it will be fully penetrating. And which unit is this well in? Is it the pumped aquifer, is an aquitard, or is an unpumped aquifer? So we'll select the pumped aquifer. Okay, now here's the well thickness. It's like 1 feet. You can leave it. It doesn't matter in this case the diameter of your well, because we are observing at a different well. If we are observing at the same well, then we need to put the actual diameter of the well, so that's how you can calculate RW, the radius of the well. Yeah. But since this is not important because we have an observation well, and what we need is like the distance to this observation well, which is about 824 feet that we saw before. And then here, this is the pumping, like, so at time 0, like when we started the test, the pumping rate was 20, 220, yeah? And let me just make this little. So this is you could have multiple pumping rates, like you step up pumping, you step down pumping. You can do this also, but in that case, we only have one pumping rate throughout our aquifer test. So let me go here. So we started at from time 0 to time 500. We only have one pumping rate, which is this number. Okay, so you do this, then you click next. And then this is the observation well. So you can call this like observation well. And we know that this is at a distance 824 feet. And you see here, it gives you this in feet. And you see here, when we enter the pumping rate, is already using the units that we selected before, which is gallon per minute. Yeah. And now here again, this is fully penetrating. It's in the pumped aquifer. The radius or the diameter of this well is also not important. And now here is telling you your data, like your data. So your data, you can go like to your Excel sheet, and this is like your data. Where is your data? That's your data here. Yeah. So that's the data at time 3, you have zero point 0.3 feet drawdown. At 500 minute, you have 10 feet, 10.9 like drawdown. So you can just copy your data, and then you come here and click paste, and then it will paste it for you. Maybe delete this one. I don't know if it will make a difference or not. The first row, I don't think it's not gonna make any difference. But make sure, so at time 3 you have zero point 0.3. Make sure you copied everything. At 500 you have 10.9. So you click, and that's it. Yeah, no errors detected in the data set. So yeah, I mean, isn't that easy and simple? Much easier than, like curve matching and substituting in the equation or anything. But anyway, now we have the data. Let's look at the data. Yeah, so the first thing you do is like you come here to view, and then like you select this one, displacement time. And here we are seeing our data. So at 3 minutes, yeah, we have like this 0.3 like drawdown. At 500 minutes, which is our last point, we have about 11-meter drawdown. So that looks fine, but let's make this looks as we are used to it. Like we are used not log linear, we are used to log log, yeah. So that now looks something familiar to us, yeah. So here, that's like uh, zero point 0.3 at like 3 minutes, and at 500 minutes we got like 11 or something here. Okay, so now we have our data. You can also select, for example, like if you come here to let me show you where to go. Uh, for math, for example, you can also play with this, like show uh, graph paper. Like for example, you can make it clean, or you can show this one. You can also make it like show it like this, but I think this is maybe this is the best view, I would say. Yeah, you wanna do this, or I think this is a very good view. Yeah, so you can keep it like this. Yeah. Okay, so now what? So now we have to select a solution. Yeah. So you go here to match like solution, and you will find by default solution will be inactive, and then you will select which solution you want. So you have confined aquifer, leaky confined aquifer, unconfined aquifer, fractured aquifer with double porosity, fractured aquifer with a single porosity. So you will select confined aquifer, and you see here so many solutions. Yeah, not only C solution. So you have like this is for C solution for recovery. This is the standard C solution. This is for step up and step pump down pumping. This is Jacob and Cooper, like the approximate C solution, and you have like all these ones, and each one would be for a different purpose. So you might like want to like this is for example if you have like a trench, a wedge shape aquifer, step down test, uniform flux horizontal well like this if you have a horizontal well. This is if you have infinite conductivity horizontal well. So you see like different solution for different purposes, but here we will just select our traditional thesis solution. Yeah, then you click OK, and that's it. Yeah, and then here now it provided it didn't solve it yet. It just like provided a solution. Now you can just do it manually as we did before. So you see here like we're trying to do it manually. See here we got like very similar number. Yeah, like 1356 and 2.1. Like so manual fit is good. Yeah, like so you can do it manually. Try to find like the best match just manually, and then it will calculate like the T for you, the S for you, or you can do it automatically. Like you can come here, match, and you say automatic. Yeah, and then when you do this, here if it will tell you about the help, like to select the optimization method and things like that. But this is not important. If I did this automatically, then I got this solution here. And again, each time you do it, you'll get a different solution. So let me try this again. Like because this is an optimization method, so it depend on here. Right? So you see, you try to do this, and then you come here, automatic. You do estimate, and you do close. Here is basically telling you that it did like so. This solution it took 7 iteration. Function evaluations 352 function evaluations. This is the RRS, the residual square error is like this much, and this is just tell you about the estimation results, the solution. Yeah, but here this is what you need. So if you want to change solution methods, we can change solution method because we know that we can also do this with not only with C's, we can also do this with Jacob and Cooper. Yeah, so if we did this, and then with Jacob and Cooper, we see we got like something very similar. You can come here, you can match automatic, you start running your optimization, and then you see you got like a very similar solution. And see, like Jacob and Cooper, it ignores this like non-linear point, and it only works on this linear point. So see, it selected like only this. It extended like your line till here to the zero drawdown. It recorded the time and substituted in the equation. So I think, yeah, that's it. Yeah, I think it's very easy. And so let's look at our solution here. So this is what we did by graphical method. We got something that looks like this. Regression method with Excel, we got something that looks like this. Regression method with Aquatisolve, we got something that looks like this. Here with Jacob and Cooper, when we did this with Excel, we got something like this with the regression method. And when we did Jacob and Cooper with Aquatisolve, we got something like this. So you see, they are all very similar. Like here, like this is 1500, this is 1400, this is 1300, 1300. So again, these numbers are all similar, like in giving the uncertainty of this problem. And here, like the S is 2 point, like it's the same order of magnitude. Like usually we are just interested in this order of magnitude, like 2.1 10 to the power minus 5, 2.1 10 to the power minus 5, 1.68 10 to the power minus 5, and 1.4 10 to the power minus. Same order of magnitude, and even same digit here. Yeah. Okay, so I think that's like how to use this method, and you can now use it for different application. Like if you have a leaky aquifer, if you have an unconfined aquifer, uh, uh, and it will you just follow the same procedure. Yeah, the details, again, the details is not important. The most important thing is like you just understand the basic concept behind them, and if you want to do this for any other case, you just learn about it once you need to do it, and then you do it. But now you know the tools. This tool is there. You know how to use it, and you understand the concept behind it. So I think that's all for this lesson. Next lesson we will briefly talk about how to design an aquifer test. Yeah. So that's it, and see you in the next video. How to design not pumping, yeah, an aquifer test. Like we'll talk about like pumping test. This is just one aquifer test, but there are other aquifer tests. So we'll talk about what other aquifer tests that are there, and how to design like an aquifer test campaign. Just briefly talk about it. So if you want to do this, you will have some insights.